Hello. In this lesson, we're going to talk about the limit of a function. To explain the limit of function intuitively, we first look at an example. In this example, we have f of x equals to x minus 1 over x squared minus 1. We know that a function is a rule that assigns each input exactly one output. So let's write down the definition of function right here, right? A function is a rule that assigns each input exactly one output. So that's the definition of a function. And for any function, we will be very interested in the domain and range. So let's take a look at the domain of this function, where we have the graph of this function. To determine the domain of this function, we're going to set x squared minus 1 equals to 0. Anything makes the denominator equal 0 should not be in the domain. So we solve this equation. We got x squared equals to 1, and we take square root on both sides. Okay, we take square root on both sides. Square root of 1 is still 1, and the square root of x squared is the absolute value of x equals to 1. And then x equals to positive 1 or negative 1. That means the domain is that x cannot be, because anything makes the denominator equals to 0 should not be in the domain. So the domain is x cannot be equals to positive 1 nor negative 1. So here we have the function. However, so we know the function is not defined. Okay, so the function is not defined at 1. Oops. It's not defined at 1, right? Of course, it's not defined at negative 1 either. So we want to see what is the behavior. Surely we cannot evaluate the function's value at 1, but we want to know the function's behavior when the input is closer to 1, right? The input could be, the input could be as close as possible. So the input could be close to 1, right? Or as close as possible to 1, even though we cannot assume the input equals to 1. So in this case, we will be looking at, from the graph, it looks like when x is getting closer and closer to 1, okay? When x is getting closer and closer to 1, the function's value, hold on, let me clean this up. So okay, hold on. I need to clean this up. Hold on. There we go. So as x is getting closer and closer to 1, right? This is the input. As x is getting closer and closer to 1, from either side, the value of the function is approaching 1, which is right here. So that's the input and that's the output that it's close to. It's close to. Even though it is never is 1, right? It never is, I'm sorry, half. Okay, this is a half. As x is getting closer and closer to 1, the function's value is getting closer and closer to 1/2. So this process, we describe it, okay? We describe this process as the limit, okay? The limit of the function as x is approaching 1, and the function we have here is approximately is 1/2. Okay, it never actually achieved 1/2, but that's the limit. That's the limit. We call this the limit of this function as x approaching 1 is equals to half. So the intuitive definition of limit is that suppose a function is defined where x is near the number. So in our example here, a is 1, but a is not in the domain, okay? It is okay, we can define the limit for a equal in the domain or not. So here in the parentheses, we explain that this means that f is defined on some open interval that contains a, except possibly at a, except possibly at a. Okay, so it may or may not be defined at a. In our case, the function is not defined at 1. Okay, then if there's a number that the function approaches to consistently, okay, so we say the limit of f of x as x approaching a equals to L. If we can make the value of f of x arbitrarily close to L, you can see in our process, right, as we are getting closer and closer to the input 1, the output is getting closer and closer to 1/2. And in the other direction, as the input is getting closer and closer to 1, right? The output, which is the red, is getting closer and closer to 1/2. Okay, let me remove this arrow. Okay, I'm going to use a line. It's getting closer and closer to 1/2. So this is the reason that for some time we want to see the behavior of the function that's, near the number that is not in the domain, or sometimes we just want to see the behavior of function, when input approaches a certain number. All right, so let's look at the definition of function one more time. Okay, so suppose f of x is defined where x is near the number a, right? So the f of x, this function is defined everywhere, but the -1 and +1, all right? And we observe the function's behavior in the neighborhood of 1, but we realize as the input getting closer and closer to 1, the limit is approaching a fixed number, which is 1/2. In this case, we say the limit of f of x as x approaching a equals L. In our example, we would say the limit of f of x, which is this function. Okay, so we're going to use the same wording. Okay, the limit of f of x, okay, as x approaches 1, oops, as x approaches 1, is 1/2. So this is how we say it. So as the input approaches a number, the output approaches half. In another graph that we know a function is a rule, right? So the input x here, right? So we have the function as a rule, f, and the output is f of x, right? In our case, as the input x approaching 1, which means to get as close as possible to 1, right? And the output f of x is approaching 1/2. So this is another way we express it, but we have now learned a new notation. Okay, for -1, it can be handled in a similar way. And the other thing we would like to mention in this case that algebraically, this can be operated, but we're going to talk about it next time, okay, in another lesson. Now, let's look at another example. This time is f of x equals to sine x over x. And obviously, domain, well, sine x's domain is all real numbers, but x is in the denominator. So the domain is x cannot be a 0. X cannot be 0. But we are interested in the behavior of the function near 0. When input is near 0, what happens, right? We cannot plug in. So we look at the graph and we notice, yeah, as x is getting closer and closer to 0, right? As x is getting closer and closer to 0, from either side, sine x over x is going to be approximate number 1, right? So you can see the value of the function is getting closer and closer to 1. So let's use this red sign. Okay, so as the input is getting closer and closer to 0, the output is getting closer and closer to 1. And we can get infinitely close. To 1. And now, and we can say the limit of this function is 1. Okay, from this graph. All right. So the limit of this function as x approaching 0, and that function, of course, is sine x over x, and the limit equals to 1. As x is approaching 0, and the wording, of course, is also similar. the limit of f of x as x approaches 0 is 1. Okay, so this is the idea of limit. Now, next we're going to introduce one-sided limit. One-sided limit. Okay, what is one-sided limit? We can see in the previous examples when we see the approaching from the graph, we can it makes no difference from either side, and we approach the input, the output approach a constant number. But sometimes it's not the case. So take an example. Okay, we're going to look at this function. Okay, then we're going to look at the definition again. Okay, so let's look at this piecewise function. And we have the graph of this piecewise function. So I'm going to bring it up here. Okay, this is the curve of the function. This is a piecewise function. And you can see the entire function is defined on the entire number line. It's defined everywhere, right? Less than 0, equal to 0, from 0 to 2, including 2, greater than 2. So it's defined everywhere. However, the rule for different input may be different, right? For example, if so I'm gonna set up some examples, right? I'm gonna set up some examples. Let's make one more row, right? For example, if I want to evaluate, and this is just to explain what this piecewise function is, right? So f of x. So if I want to know what is negative 8, right? Negative 8 as the input is less than 0. So we're going to apply this rule. And so that's going to be negative 8. Okay. And that equals to negative, the cubic root of negative 8 is negative 2. Negative of negative 2 is positive 2. Now, for f of 0, how about for f of 0? F of 0. F of 0, we are told, equals to 1. Equals to 1, right? Because we have one specific rule just for x equals 0. So now what if we want to find what is f of 1? Well, 1 is, you check 1 is not in this interval, not in this interval, it's in this interval. We're going to use this rule, and that rule is 1 squared. So that equals to 1. Okay. And how about f of, say, 3? F of 3, obviously, the last rule applies. So when x equals to 3, we apply the rule that is for it. In this case, it's going to be 4. Right? So for input in different intervals, the rules are different. Now, suppose I'm interested in 2. I want to see the function's behavior near 2. And then you have to ask me, is the input approaching 2 from left or from right of 2? Because the rules are different. If x is approaching 2 from left, okay, how do we express that? Well, if we're approaching 2 from left, the limit, obviously we're going to use this rule. And this rule is going to take us to the answer. So let's write it down. Okay, limit as x approaching 2, but from smaller than 2. From smaller than 2. Okay, so let's write it down. Limit as x approaching 2, but from smaller than 2. Okay, limit as x approaching 2, but from smaller than 2. Okay, limit as x approaching 2, but from smaller than 2. Okay, limit as x approaching 2, but from smaller than 2. Okay, limit as x approaching 2, but from smaller than 2. Okay, I'm gonna make the fonts a bit larger. We're gonna approaching 2 from smaller than 2. How do we make a distinction that we're approaching 2 from left, or are we approaching 2 from right? Right? So here we want to look at limit from left or limit from right. And so we must have a notation to specify this. So since now we're approaching 2 from smaller than 2, we're going to put a little negative sign on the shoulder of 2. And for this function, as x approaching 2 from smaller than 2, we know that this rule is being used, and that is x squared. Okay, and that is x squared, of course, is equals to 4 from the picture. Okay, then you understand if we are interested in the input approaching from right of 2, right? So the limit of the function when the input approaching 2 from larger than 2, so we put a positive sign on the shoulder, and then the limit of f of x is going to be right here is going to be 1. Now we can see the limit from left and the limit from right are not the same. Now the question is, since the limit from left and from the right are not the same, and we say the limit when x approaching 2 does not exist. Okay, so in this case, so that brings us to not only one-sided limit, okay, not only one-sided limit, hold on, let me clean this up, right? Not only one-sided limit. Definition of one-sided limit we write, right? This notation, we say left-hand limit of f of x as x approaching a, or the limit of f of x as x approaching a from the left or from smaller size is equal to L. If we can make the value of f of x arbitrarily close to L by taking x to be sufficiently close to a with x less than a. So we're approaching it from the smaller side, approaching it from the smaller side. And the right side limit, of course, is similarly defined. And now we have another important result, okay? If the limit exists, x approaching a, if and only if the approach of input from left and from right will end up with the same limit. If one of them is not true, then there's not a limit. So that's how we decide that this limit, right? So let's see how we use the language. So the limit as x approaching 2, whoops, as x approaching 2, f of x, okay, this limit does not exist. Reason, since these two limits, since the limit from the left is not the same as the limit from right. Okay, if we compare this, right, so let me bring this up to bring this higher, right, one-sided limit. I'm going to put this one-sided limit right here, right? We got a one-sided limit notation. And now we have limit from left, limit from right are not the same. Therefore, the limit does not exist. All right. Okay, let's look at some other examples that, with functions that we're familiar with applying our new concept. This is the graph of 1 over x, right? This function is very, very commonly seen. And we have the graph, right? So we have 4 directions, right? Obviously, the domain is x cannot be 0. X cannot be 0, right? X cannot be 0. So in the direction on this side, as x is approaching positive infinity, keep going, right? The limit as x approaching positive infinity (1 over x) is equal to 0, right? And we can see the curve is getting lower and lower, but always above x-axis. And in the other direction, as x approaching negative infinity, right? If x approaching negative infinity, which is on the other side, is 1 over x. This time it's approaching 0, but from smaller than 0. So we got our notation. Now, then you say, how about the other 2 directions? What if we want to see the behavior of the function as x is getting closer and closer to 0? Well, here we go. When we want to see the limit of f of x as x is approaching 0, and obviously you can see as x approaching 0, okay, as x approaching 0, and the y, the output is approaching positive infinity in this direction. So we have to make a distinction. So when x is approaching 0, from greater than 0, 1 over x. 1 over x is positive infinity. Is infinity a limit? Infinity and limit seem to be contradictory, but we do introduce the concept of infinite limit, primarily in the case of vertical asymptote. Okay, you guys might have remembered that concept, right? So let's write down the other one before we introduce the definition. So limit as x is approaching 0 from smaller than 0, 1 over x is approaching negative infinity, right? You can see as from the graph, right, as x is approaching 0 from smaller than 0, the output is getting lower and lower, infinitely lower, negative infinity. So these are the 2 cases, and we introduce the concept of infinite limit. That sounds very contradictory, okay? But we do have a definition to illustrate this, primarily for the purpose of vertical asymptote, most of the time, okay? Now, so let's look at this definition. Okay, the intuitive definition of infinite limit. Let f of x be a function defined on both sides of a, except possibly at a, which is similar, then the limit of the function as x approaching a is infinity means that the value of f of x can be made arbitrarily large as possible, as we please, by taking x sufficiently close to a but not equals to a. Okay, so look at the other example. The other example, as you can see, as x approaching I'm trying to use the same color. I'm trying to use the same color for input, right? As the input approaching 0 from either side, the output is approaching positive infinity consistently. So this is an example of as the limit, okay, limit as x approaching 0, the limit on either side is going to be approaching positive infinity. And in fact, it is a description of a vertical asymptote, So now by this time, we can move on to the next step. Okay, we look at some more examples like tangent x, right? Tangent x, one, take this vertical line is x equals to pi over 2. As you can see, right, the limit as x approaching pi over 2, right? Approaching pi over 2 from which side? From smaller than pi over 2 side. Okay. From smaller than pi over 2 side in this direction. So we're going to have to use our notation. And that limit is positive infinity. If it's a positive infinity, you can omit the sign. And if the limit is to x approaching pi over 2 from larger than pi over 2, hold on, then it's negative infinity. And you can see these are also the vertical asymptotes. All right. And for arctangent, we also see some cases. We have two cases, right? We have two cases. One is as x approaching positive infinity, right? So we're gonna write it down using these notations, and I would like you guys to follow me and learn these new notations. So as the limit, so from the picture, as we can see as x approaching infinity, arctangent is that's approaching positive infinity in this direction, right? In this direction, right? The curve is getting higher and higher, approaching pi over 2. And of course, in the other direction, which is when x is approaching negative infinity, right? So it approaches negative pi over 2. So when we approach this negative infinity, that's going to be negative pi over 2. So we're getting pretty familiar with the notation. Okay. I'm gonna bring this over here. All right. So you can see the vertical asymptote definition formally introduced here, right? We've seen the tangent case, we have seen 1 over x case, we have seen 1 over x squared case, and next we're gonna see this other case, which is ln x, natural log x. The vertical asymptote is right here, right? It's y-axis. So the definition of vertical asymptote, a vertical line, x equals a is called a vertical asymptote if at least one of the following statement is true. At least one of the following statement is true, right? Say, for example, in this case, one of the cases is true, right? So I'm going to bring this picture just a little smaller, right? So we can see the limit. We know the domain is x is greater than 0. So when we want to see the limit, the behavior of the function, right, as x approaching 0, and of course has to be from larger than 0, right? So then ln x is going to be approaching negative infinity. And one of these is true because we only need at least one. So only this, so this situation is satisfied, therefore it's vertical asymptote. So the vertical asymptote of course is x equals 0. All right. And if we take this definition, and we apply this definition to all of these cases, right? Because only need one condition is be satisfied. Only one of it is satisfied. Then say if I put it here, right? You can see in the tangent case, pi over 2 is a vertical asymptote when x is approaching pi over 2 from smaller than, right? From smaller than is positive infinity, larger than is negative infinity. So two of them are satisfied. So pi over 2 is a vertical asymptote. Okay, and this same definition applies to this case, which is approaching positive infinity, and also applies here, which is for x equals 0 is a vertical asymptote. All right. I think that's all for this lesson. Thank you for watching.